Hello, welcome back. Now, in order for us to really understand how we are going to use molecular dynamics for these two specific complex physical problems, one in the area of adhesion of ice on metallic surface, another one is micro tribology or what we call molecular tribology. We first remind ourselves very quickly the unique properties of molecular dynamics. As you know, by now we all know that unified study of all physical properties, thermodynamic, structural, mechanical, vibrational and transport properties, we can use our molecular dynamics technique. And we also understand that with only 100 atoms often sufficient to simulate the bulk properties of the material using our familiar periodic boundary condition. And we can use deterministic and reversible system simulations in order to understand. So, we are not making assumption, it is deterministic and it is using the second law of motion solving the Newton's equation of motion. We have complete control on all the parameters once we set up our system. So, we can change temperature, pressure, volume, all kinds of stuff that we have done throughout our course using our virtual molecular dynamics lab. And then we also have atomic trajectories. So, now that we have ensemble of these trajectories and understanding of the thermodynamic ensembles, which a lot of people do not understand. So, you are in a unique position now that you understand the thermodynamic ensembles like microcanonical ensemble, canonical ensemble, isobaric isothermal ensemble and grand canonical ensemble. With that understanding and the trajectories, you can calculate the properties of your interest. So, now you can solve this investigation in a complex physical phenomena almost like a detective and see what is going on in this particular case. And that is what a scientist is. Scientist is like a detective who is trying to figure out why nature is behaving in a certain way. So, let us put on our hats of scientific investigators and look at what do we need to investigate these two problems that I am going to talk about. So, let us look at the first case study now. First, number one thing that we all need is we need a potential energy functions. So, as you see on your slide, I put a very generic model that we are all very familiar now, which is called Lennard-Jones function. Your favorite function that you will always use in order to create some of the molecular dynamics models. So, this is where we have only two parameters, as we now know with our study of potential energy function, that we only need two parameters for this function, and it has 1 over r to the power 12, which is the repulsive part, and 1 over r to the power 6, which is the attractive part. And that is where if you look at on your slide, you have this potential energy well, and a particle can remain very happy at the bottom of the potential energy well, because it is the minimum. And as you heat it up, it starts vibrating and then it goes out, and at certain point it will break out of the bond and break the bond. And those two parameters are epsilon, which is the potential energy parameter, and sigma, which is nothing but the lattice constant of the material. And we looked at argon, xenon, krypton, all of that can be simulated very well with Lennard-Jones. But Lennard-Jones is a very common formulation for any kind of material, and you will see in the case studies that how we use Lennard-Jones formula or the mathematical formula, but with different parameters in order to understand non-bonded interactions. Now, if you go the second part, because we are going to do ice study, we need to have a model for water. We have learned that simple point charge model, where we are going to put charges around the oxygen and two hydrogen atoms. But we also now know that in this triangular molecule, you have certain angular connectivity between the two hydrogen atoms connecting to the central oxygen atom, and that is where you see on your slide that there is an angle to the connectivity. And if you look at oxygen and oxygen point to each other, in between there is one hydrogen, which creates what we call hydrogen bond, which is a kind of van der Waals force that you have learnt about in this course. So, now we are connecting for our investigation bonded as well as non-bonded. So, the bonded part comes from the two hydrogen atoms connecting to oxygen, and they have stretching they have bending, and they have rotation. So, now we connect all of these together. Again, this is a simplified SPC, simple point charge material, where you understand one part is Lennard-Jones between oxygen and oxygen, second part is Coulomb, which is between the charges, and the third part is we are looking at Coulomb interaction at certain distances. And we are going to use a much more well defined Toucan and Rahman's presentation of SPC extended potential, where we consider all bonded and non-bonded potential. But now, because we are going to also put this water layer or ice layer on top of a particular copper surface, which is a metallic surface, we could have picked up copper, aluminum, different kinds of FCC structures including gold. So, what we are now going to use copper, because most of the electrical wires are made out of copper and aluminum, which are almost similar in nature, and because we want to know how we can reduce adhesion of ice on these long transmission cables, we have looked at copper here. So, in copper I now need to remind that there is an inner core, and then there is valence electrons because it is metallic. That is where we use EAM potential, which is many body potential, and in EAM potential we have two things. One is the embedding function, which has electron density. So, we are using density approximations. So, that is what we call approximation, which is look at the density function. And so, the density of electronic function changes or locations of the atoms, and those electronic cloud and their densities is essentially approximation. And then you have a pair potential part, which is the repulsive part. So, you have cohesive part and repulsive parts, and the total cohesion energy comes out of these two repulsion and attraction parts. So, that is how we are going to take copper and simulate that using EAM potential. And then, as I said in the second part of our case studies, we are also going to look at silicon potential. So, this is the 3 body potential function. So, we also need to look at now not only potential between particle 1 and 2, but also particle 1, 2 and 3, and that is where this becomes 3 body potential, and that is where Stillinger and Rahman created their one of the first potential. And finally, for this study we do need interface potential. So, I need to talk a little bit about this interface potential. What happens when you have a copper material, let us say a metal surface which has conduction electrons. So, you have this electronic cloud at the surface, which is responsible for electrical conductivity, thermal conductivity, and that is why these metals have much higher electrical and thermal conductivity because of these conduction electrons. So, they can really move stuff very quickly as compared to insulators, where you do not have any conduction electrons. So, the electricity does not pass through. So, if you look at that material, and now we are putting water, which has charges as well. But if you look at if it is a pure water, it is electrically neutral, because the charges on oxygen atom, which is 0.82 electron volts, and that is the negative charge, is balanced by the 2 hydrogen positive, or what we call proton charges, which is positive 0.41. So, essentially electrically it is negative, but as soon as that particle now goes on top of the copper, now this conduction electrons are going to start interacting with the electronic cloud of the hydrogen atoms, which are very light and protonic material. So, that is where now the question is how do I treat that interface potential function? And let me tell you, that is not an easy task. So, in this case we have to really work on some of the quantum mechanical models of the clusters. So, we use a particular method called SCF-LCAO, which is what stands for a self-consistent field linear atomic orbital theory. So, we are going to essentially look at these atomic orbitals. As you know, every atom has a nucleus and these electronic orbitals sp and d and f orbitals, which are getting out, and you are filling up electronic shells. So, these electrons now are going to interact with the conduction electrons. So, you have to now take care of that. So, if you look at on your slide, this is the potential function that I came up with for this interface between copper and oxygen. So, you have a potential between oxygen and copper, water and copper potential, where oxygen and copper and hydrogen and copper and second hydrogen and copper. Then you also have hydrogen and copper with along with another function, which is a distance function between the two atoms. We will talk more about it when we get to that, but with some of these exponential functions we are able to very accurately understand the binding energy between the water molecule and the copper surface, and that is how the interface potential is created, and most of the problems you will encounter interface. So, now we are ready to jump into our case study. Thank you.